So today I want to change a little the subject, and you will see what I will say today. It's still connected with what we were discussing in the previous lectures, but in a more subtle way. So today I actually prepared, as I told you yesterday, the lecture a bit shorter to have more discussion at the end, especially when we finished all the 3 lectures, so the picture is say complete. And just for completeness, today in the previous lecture I focused a lot on the dynamics of shear waves. So I focused a lot on basically the dispersion relation of shear waves in liquids. And today I want to try to tell you a bit more about other questions about liquids that are of course connected to the dispersion relation of the low energy modes, but that involves more thermodynamic quantities. So in particular today I want to discuss two things. The first thing is the density of states of vibrational modes in liquids. And I want to discuss something about the specific heat of liquid. So let me start. Okay, so these are the 2 problems that I want to address today. So on the left, you can see the typical density of states that you can obtain in liquids, usually, for example, from simulations, diagonalizing the Hessian matrix, but also like from experiment, doing, for example, neutron scattering experiment or other type of probes. And what you see here, it's something that is very different from the solid counterparts. And in particular, remember from the first lecture that if you are a solid, at low frequency, your density of states will follow a law, which is called Debye law, which tells you that density of states is quadratic in the frequency. So in all the solids, and I show a plot, for example, in the first lecture, you will see that at low frequency, this curve starts quadratically, and then they go up to a point, which is more or less in a solid is what corresponds to the Van 't Hoff singularity, so the edge of the band, and then of course they will drop down after a certain frequency, microscopic frequency. Now in liquids, as you see, the situation is very different, and it's very different because the density of states at low frequency is not quadratic, it's actually linear. And here you can see a plot. This is a plot taken from a simulation paper. So the dots are simulation data at different temperature, and all in the liquid state. And you can see that all of them, they are kind of well approximated by a linear slope at low frequency up to basically some certain maximum that then appear. So the question that I want to address today, at least the first question that I want to ask today, is how can we understand this difference between solids and liquid, and why the density of states of liquids is actually linear in frequency. So where this linear in frequency contribution come from? And the second question, which is of course related to this plot that you see on the left, it is about the heat capacity. So as we discussed in the first lecture, the heat capacity of solids is very well understood, and it follows, again, the Debye law, or if you want to complete it quantum mechanically, you follow Einstein model. And what you see is that at low temperature, if you are in 3-dimensional bulk solid, you will find that the specific heat grows like T to the cube. And then at a certain point, of course, at what we call the Debye temperature, it will basically flatten, and it will asymptote what is the Dulong-Petit law. Now, as you can see on the right, so here there are basically some experimental data of a certain liquid. So you can see that the specific heat of liquids is totally opposite of solids. So not only the specific heat of liquid does not grow with like the cube power of the temperature, but it doesn't even grow at all. So the specific heat of liquids does not grow with temperature, but it decreases with temperature. And you can see the slope of this decrease depends on the liquids that you are considering. And more or less, when you go at very high temperature, of course, you have again to recover basically the Dulong-Petit law. And you see that basically all these guys are asymptotes to a constant. Of course, some soon and some a bit later. but basically this is the general trend. So this is the general trend that you see in the specific heat of liquid. Now, what I want to tell you today is how can we understand, or at least try to understand, this feature from theory. So what can we do? Where's my slide? Okay, so one of the most important feature of liquids that distinguish them from solids is that liquids are highly anharmonic. So if you see at the potential landscape of the liquid, it looks something like this. So you can see that it is definitely not, a nice periodic potential. There are many barriers, and all these energy barriers are distributed in a certain ways. And you can see there are barriers which are large, barriers that are a bit small, and the things the landscape is totally anharmonic and totally disordered. And you can see that there are a lot of points which are actually not minima, but are saddle points. So you see there are a lot of maxima that appears everywhere, and these maxima are related to these energy barriers. And there are many of them. So now the idea, which is kind of natural, is can we understand more of the dynamics of liquid just looking at basically how the potential look like? And here I have to remind you that basically what you usually do in the context of solids, you define what is called the Hessian matrix, which is this object which you find up here, which is nothing else than the second derivative of the potential with respect to the position of the atoms, and of course for every atoms. And then what you do, you diagonalize this matrix, and you compute the eigenvalues. So this is what you are doing here. And then these eigenvalues can be converted in frequencies just by using basically this definition. And these omega n here are nothing else than what we call the normal modes, or the normal frequency of the solids. Now, this is very clear for a solid, and it's used everywhere to basically understand what is the vibrational spectrum of your solid. But what you can see is that in liquid, actually the situation is more complicated than that. And it's more complicated than that for two reasons. So the first reason, which is very important, is that in a liquid, the first derivative of the potential with respect to the position will not vanish. So in general, if you wait long enough, you will have forces, and your particle will move from the equilibrium position. But still, if you consider short time scale, and I will be more precise what this short time scale means, you can still think about that term to be basically irrelevant, and you can try still to diagonalize this matrix, even if you are in a liquid. Now, what you find surprising is that when you diagonalize this matrix, you find two types of eigenmodes. So you find basically modes. Sorry, here is a typo, by the way. So this should be omega, should not be lambda. I'm very sorry about that. So you find basically eigenvalues which are positive, so which corresponds to basically real frequencies, and these are called normal modes. So again, this is omega squared larger than 0. But you also find eigenvalues which are negative. So eigenvalues which are negative means that the frequency is purely imaginary. So these are modes that want to relax. They don't want to propagate. And these are called in the literature instantaneous normal modes. So naively, you can think that this lambda, and therefore omega squared, is related to the curvature of the potential. So modes which have lambda positive and therefore omega real, they correspond to vibration around minima of the potential. So this is exactly the same of what we define as elastic vibration, like in a solid. But since there are many of these saddle points, there are in the liquid, especially when you increase the temperature, there are many modes that do a different type of behavior, which is this kind of behavior. So these modes are basically probing regions of the landscape where the curvature is negative. And therefore, when they are basically probing this kind of region, what they do, they will just relax back to equilibrium. So they will fall down, if you like, doing a mechanical analogy, and they will go down to equilibrium. So the frequency or corresponding to this kind of motion is not a real frequency, because here there's no propagation or oscillations. Here you're just falling down and relaxing. So this process corresponds to basically a lambda, which is negative, and an omega, which is purely imaginary. Now, I'm sorry, but my connection today, I think, is very slow. So then these inhomogeneous instantaneous normal mode are observed in many simulations. And as you can imagine, these kind of modes that you see disappear when the system becomes solid. So here I want to show you one paper. There are many. I just choose one because the plot is particularly illuminating. So what you see here is the density in function of the frequency, and this is a customary thing on the left. So on the negative axis, you plot the density of the modes which are instantaneous. So what was frequency is actually imaginary. And on the right, you plot all the rest, so all the sum, all the modes. So this is the full density, okay? And this is the density of states only of the modes which are relaxational. So what frequency is imaginary. And here you can see that basically you are moving your temperature, and basically you are going to from high temperature, so over here, to basically low temperature. So you are basically going towards the solid, if you like, towards the solidification temperature. And what you see is that the important thing to observe in this plot is this left part. So you see that the amount of modes which are relaxational decreases with the temperature, and it actually dies when the system becomes solid. So when you reach the solidification temperature, which is what we know, because we know that in a solid, you will not see any of this mode. So now what we want to understand, therefore, it's kind of logical, and here actually you can see another simulations where this is also clear. So here, instead of moving the temperature, they are moving actually the density. So they're making the system solid by moving the density. The density is rho. And you can see here, so here is more clear. So on the left, there are frequencies which are imaginary. So basically what people plot is I omega, which means that basically these are all the instantaneous normal modes. And on the left, people plot the other part, what they're called the normal modes. So what you can see here is something very interesting. So let's go down here. Okay, so if you go down, you see that on the left, there is absolutely nothing. So basically, instantaneous normal mode are not there. And you see that the density of states, the full density of state, is very quadratic, you see? So at least a low frequency is quadratic. So this is what you expect in a solid, and this can be explained by Debye theory, very simply. But now look, when you go to a liquid, you see that basically there is an additional part, which are these instantaneous normal mode, which at low frequency, you have to see on this side, they are linear. And then they grow, and they grow when you become more liquid. And you can see that then the full density of state is not anymore quadratic, because of course there is this contribution, which is linear, which wins at low frequency. And you can see that in intermediate step, you still see the linear, but then you see that there is a quadratic getting in. Okay, so this means that the linear part is not strong enough yet to basically dominate all this response up to here. And this is basically what you see from, let's say, moving from what you call a perfect solid or an ordered solid to something which is liquid. So the density, the dynamics of the density of state is what is pictured here in this slide. Now, so the idea, the main idea is, what is the role of these modes? And remember, at least from a phenomenological perspective, the mode, so a single mode, will have a frequency which is purely imaginary. All right, and the value of this imaginary part, it's actually related to the saddle point with negative curvature, and of course it has to do a lot with anharmonicity. So for the moment, I'm not attempting any microscopic description of what is actually this guy here. I'm just asking myself something simpler. I'm like, okay, imagine I have a mode that behaves in this way. What is the density of state? So how can I compute the density of state from something like that? So if you're familiar with this, actually, let me say a few things historically before moving to the computation. So this idea that there is basically a linear part in the density of states of liquid, it's old. And here you can see, for example, two papers by Tom Keyes which is one of the expert in the topic, and already in 1994 and 1997, so he observed numerically from the fit that the density of states that here he called rho of omega t, he said, well, okay, when I take my data and I try to fit them, fortunately, the full fit, so no matter what temperature I'm looking at, no matter what system, I always get B more or less 1. Okay? So this means, and that is what he writes here, that this kind of ansatz, which as you can see at low frequency is linear in frequency, give excellent results. And he does this observation not only there, but in other paper, where again he sees that the experimental data, this time are experimental data, consists of a term which is omega times some exponential. So again, at low frequency, this is again basically linear in frequency. But you can see that these are just empirical observations. So you can see here empirical fit. So the idea that of course there was this linear in omega term, it's old. But from a theoretical point of view, this is not very satisfactory. But let me emphasize again that the idea is not new. And again, there are other papers here, and probably many more that I forgot to mention that there is this transition. So here, not only that, but here there is written explicitly that the density of frequency is linear in omega, rather than omega squared as Debye like. And here you see there is the first, at least to my understanding, indication that these modes can be responsible for that. Here, indeed, there is no reason why instantaneous normal mode should have the sound wave-like properties needed to generate Debye behavior. So the idea, the physical idea, was there in the paper, and it's growing, and it's like that these modes, this instantaneous normal mode, might be the responsible for this linear behavior. But unfortunately, making a theory of this, it's hard, and I will explain you why. So basically, so far, a closed form derivation of these things is missing, even though there are many complicated models that try to do that. And here I mentioned some of them. Most likely, there are many more. But none of them can get to this formula in a very simple way and just using, a 2 lines derivation. And that's what we did with my colleague Alessio Zaccone just well, almost 1 year now, well, a few months ago. And this is this paper that is published in Venus, and you can have a look. And so what did we do? So we did something very simple. What is the big problem of solving or computing the density of states for a mode which is imaginary? So the big problem is that usually when you compute the density of states, and here is the definition, you sum basically all the frequency, and every frequency comes with basically a delta function. So you will have a delta function of all the eigenvalues. And then, okay, if you want, of course, if you have many of them, you can basically transform this sum here into the continuous, and basically replace this with an integral and get basically your density of states. Now, what is standardly used here is what is called the Pleimeji identity. So the Pleimeji identity is just noticing that you can rewrite this delta function as the imaginary part of the green function related to this mode. So this comes from basically standard theorems in complex algebra or in complex numbers. And but there is a problem. So the big problem is that the original Pleimeji identity is actually valid only when this frequency here is real. So you see, on the contrary, that our instantaneous normal mode, if you consider the green function of this mode, what you see is that this green function should look like something like that, where the pole is basically your mode, but this green function is definitely not real, and the pole is not real at all. And that's exactly where all the papers before were stopping. So the paper before were stopping exactly this formula, saying, well, okay, now omega j here, in the case of instantaneous normal mode, it's a complex number, actually purely imaginary number. And therefore, I don't know how to compute this thing. I'm stuck, okay? So now, luckily, our mathematician colleague thought about these problems before us, and at least the first mathematical papers where this is discussed are these two papers here from 2010 and 2016. This is a collaboration of Spanish mathematician, which you see is published in some mathematical journal. And what they did is basically they considered the problem of the complex Pleimeji identity. So you see here the paper is called the complex Dirac delta and Pleimeji formulas. And here you can see also why they were interested. They were interested for something very simple and very similar, which is basically how to describe barriers, energy barriers. And this is not surprising because, as I told you, basically these kind of modes are nothing else than modes where you jump energy barriers. So in this paper here, these guys discuss how to generalize the Pleimeji identity to basically a complex plane. So what we did is very simple. I don't want to enter into the mathematical detail, but basically we took their formula, we studied their formula, and we applied to these modes here. So if you do that, you will find something which actually is extremely simple, and you will find that the density of states, or the final density of states, look like for one mode, something like that. So why this formula is nice? Well, this formula is nice because you can see immediately that basically the linear part at low frequency, this guy is linear. Not only that, but then there is a maximum, which is more or less when omega is equal gamma, and then this thing goes down. And not only that, but you see the simple formula also tells us something about what is the coefficient of the linear term. Because the coefficient of the linear term is exactly 1 over the imaginary part square of the mode. So remember, this is nothing else than how fast basically this relaxation or this barrier jumping is happening in liquids. And indeed, we will see that basically this explains also the temperature dependence of this coefficient. So then what we did is, we tried just to see what would happen with some simple simulations data. And here are the simulations data. And in red is basically our, with the line is basically our formulas. And of course, you see that the data at small frequency are all linear, and then they get up to a maximum, and then the data goes down. Now, take into account that of course our formula is extremely simple, and it does not hold at all at large frequency, and you can see this even more clearly in the red data. So the reason why the red data are much worse approximated than the others is that you are going towards a solid. Actually, rho star equal 1 is exactly the solidification density. So going from red to, from green to red, you're going from a liquid to a solid. And indeed, you can see that our formula fits worse and worse and worse. And you can even see that there are some relics of Van Hoff singularities appearing here. So these are relics of Van Hoff singularities. Now, also, we did another analysis, which is, to try to make sense of what we wanted to do. Okay, and which was like we took some data at different temperatures. So these are also simulations data at different temperature, which are available in the literature, and we try to match them. So here are all in the liquid state, and actually very, very deep in the liquid state. And you see that the fits indeed are much, much better than what I showed you before. But you see also another things, which is that increasing the temperature, you see that basically the linear slope is going down. And then you can try to understand what this means. So this means, in our formula, this means, remember the linear slope was 1 over gamma squared. And therefore, what we can do, we can basically extract what is the dependence of gamma from basically in function of the temperature. What is happening? Do you guys see the slides? I don't see any slide.
It's okay. It's okay. I see at least.
Okay, then let me try to go back and go from, because I cannot see it. Okay, now it appears. Sorry. So then what you can do, you can basically extrapolate from our data, from the data, what is the dependence of temperature. So here you can see, unfortunately, this data, they have only 3 points, so you cannot claim much. But just for fun, we try to see, and it looks like that this gamma, so this relaxation time, sorry, relaxation rate, it's following some kind of Arrhenius law. Now, this is very preliminary, so we're actually doing a much more precise analysis on the coefficient. But basically, the aim of the first paper that we had was not really to understand, the coefficient itself, was really to give a derivation of this linear infrequency in the density of states. And of course, there are many questions that here can arise. Okay, so and the conclusions of this part is that basically this universal linear infrequency scaling in liquids comes exactly from the instantaneous normal modes, as people were already saying in the 90s. And now we are happy because basically we are able to derive this formally and rigorously from math for the first time. So of course, those people were right. They were totally right. And we can prove it now just using basically these mathematical tools that our mathematician's colleague gave us. So, why so slow? I'm sorry, but okay. So then a natural question, which is like the next question is, all right. So we have understood, and actually was well known already before our work, that these instantaneous normal mode, they have a very strong impact on the dynamics of liquids, and they are actually dominating the response at low frequency. Now, the question that I want to address now is, what is the role in the specific heat of liquids? So is it actually related? Is it completely null or what? So as you probably know, that from a theoretical point of view, understanding the specific heat of liquids is extremely difficult. And to my understanding, there is only one theory over there, and it's still quite controversial. So I will mention it after, and we can discuss it later. So, well, our idea was very simple. Was like, okay, can we just take the result that we obtained before and use it to compute the specific heat? So very blindly, we thought about these modes like if they were like bosonic modes. And so what we did, we just plug the density of state that we found, which is what this density of state that you can see over here. So for simplicity, we just put an exponential cutoff, which actually our theory does not predict, but is necessary to basically cut this density of state at large frequency. But as you will see, basically the results are actually not depending at all on this cutoff. And then what we did a simple assumption, which of course is very simple, but it's kind of corroborated by the data, which is that oh, can you hear me now?
Yes, Matteo, no, it's okay.
I'm very sorry. I'm very sorry, but today I don't know what's happening. The connection is very bad. So just let me know if the sound is not good, and I will stop and improve it. So yeah, I was saying that as a first like theoretical check, what we want to do is just like plugging the density of states that we obtain analytically, and put like a phenomenological answer, this Arrhenius law, and then compute the specific heat. Okay, so this is what we basically do. I cannot change the slide. What is happening? Ah, all right. Thanks. Now I can. So then we computed this specific heat, and these are the results. So this is the contribution to the specific heat of the instantaneous normal mode. Okay, so here we consider only the instantaneous normal mode, and we try to ask ourselves what is the specific heat that comes from this mode. And here you can see something which is very interesting, because what you see is that the specific heat decreases with temperature. So the contribution of this instantaneous normal mode goes down with temperature is totally different from the contribution of phonons. And what you see here is two things. So first thing is that the larger this relaxation rate, the less is the specific heat. So these guys contribute less and less to this specific heat. And the other things that you can see here is that basically the curvature of this specific heat depends strongly, or at least we can correlate it with the energy barrier. So it looks like there is a correlation that the smaller the energy barrier, the fastest the specific heat drops down with temperature, and the highest, the slowest. So you can see here. Now, of course, one thing that we can try, and this is basically just, again, a phenomenological picture, is what about trying to fit some data? So what we did, we took a bunch of liquids, and we assume, and this is, of course, an assumption, and importantly, we will discuss this. So we do not consider any phonon contribution. Okay. The reason why is that because at low frequency there are no phonons. One can ask, or shear waves, one can ask himself if actually when you go to very high frequency, so very high energy, actually the modes, like the shear waves that appear after the K gap, can actually contribute or not. And here what you can see is that we fitted a bunch of liquids, simple liquids, and the important thing is that the fit has only one free parameter. So we use the Debye temperature, sorry, the Debye frequency, which is given by basically this list, which is all known for these simple liquids. We also took the energy barrier. So the energy barrier for these liquids is also known because these are simple and liquids, and we took the energy barrier, which is the standard one, like in the potential. And so the only things which actually is kind of unknown is this parameter, which is not known from experiments or from any data, and we just fit that. So what you see here is the following. So look, for example, one thing. Look at xenon, the blue curve, and look at neon. So neon drops much faster than xenon. Now look at the energy barrier. This is the energy barrier in the Lennard-Jones potential for xenon and neon. There is almost a factor of 10 of difference. So the energy barrier of neon is much, much smaller than the energy barrier of xenon. And you can see that the drops, indeed, these are data. So the colors are experimental data. The data drops down much, much faster than in xenon. So it looks like that at least qualitatively, our theory match with what you see. So the data are matching. And what you see is that basically xenon, so liquids where the energy barrier is larger, like xenon, they basically drop down much, much slower. And here you can see other examples. So actually you can try to put in order, and you will see that the curvature works exactly that way. So basically the fastest one is neon, which has 33 in Kelvin, the energy barrier. Then the next one is our yellow line, which is under 2. And then you find things which you see is the second fastest. And then you go faster, slower and slower and slower. So this, of course, is qualitative, but it's a kind of nice match between at least the simple argument and the data. So now the question is the following: is this feature that we see in experiment, that the specific heat decreases with temperature, a feature which comes indeed from the instantaneous normal mode, and which explains the big difference with solids, where the theory is given by Debye, but remember, Debye theory for specific heat is based on phonons. So basically, phonons behave totally different from these modes that I was describing, and phonons basically give you a specific heat which grows with temperature, while these modes give you a specific heat that decreases with temperature. Now, of course, this analysis is it's still very preliminary, and there's a lot of things to do. And let me say a few words about what I think can be done and should be done. Again, why? What is happening again? Do you see the slides? I don't see the slide again. Let me.
Matteo, I see.
You see? Okay, then let me try to. Okay, now I see it. Sorry again. So then, what is the theoretical alternative? So there is one theory model, which is actually presented in this paper. It's quite old. It's almost 10 years. And probably most of you know this theory. So this theory is called the Phonon theory of liquid thermodynamics. And it's basically, the idea is to use what we used in the first lecture, or actually even in the second, this K-gap dynamics, to understand if Phonon, because of this K-gap dynamics, can actually give a contribution to the specific heat. And so what these people prove is basically that if you consider the shear waves dynamics in liquids as given by the K-gaps, you actually also see that the specific heat, also the Phonon part, is not growing, but also the Phonon part is decreasing with temperature. Now, and of course, they can fit also as well a lot of specific heat data. So now the question is the following. So the first question is, which of the two theories is correct, or are they actually both correct? And from a very naive perspective, since in liquids there are both normal modes, or phonons, let's call it, and instantaneous normal mode, it's kind of obvious that both of them should contribute to the heat capacity. And indeed, what we nicely see is that from this paper, the phonons contribute exactly as something that decreases with temperature, but also the instantaneous normal mode contribute exactly in the same way. So now the question which is left, and I think is an interesting question to ask with both with simulations and possibly also with experiment, is which one of these two contributions is actually dominant? And obviously, one can expect that which of the contribution is dominant, it will depend on the temperature. So the reason why it will depend on the temperature, think about it, is you have to think again about the K-gap. So if you are at small temperature, the K-gap is small, all right? So at very low momenta, you will have immediately phonons which propagate, shear waves which propagate. So it's understandable that when you are basically at low temperature, the phonon contribution to the specific heat should be large, because you have a lot of phonons at low temperature and sorry, at low momenta. Now, on the contrary, when you go to high temperature and this gap opens, you have a big window where basically there's nobody propagating. And in that window is exactly where this instantaneous normal mode can be active. Because it's true, the K-gap is telling you, look, you don't have any collective shear propagating mode below some certain momentum. But nobody is telling you that you have modes which are relaxing in that window. So the question is like how to interpolate between the two, and how can you understand the full picture of the specific heat in terms of basically these two different contributions that come from two different effects. And so, of course, the last, let's say, the final target, which it's I think it's maybe a bit ambitious for the moment, but it's basically the long-term goal. I mean, what should be, one would like in general to be able to reconstruct, or at least to understand at any temperature in, let's say, the phase diagram, which are the main contribution to the specific heat. And as you can imagine, it's very, 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 very likely that the specific heat, so the contribution to the specific heat, can be understood in terms of which are the excitations which dominate the response at any temperature. So in a way, one should be able, from the density of states of the modes, to understand which kind of mode is actually the most important at a given temperature and reflect these properties in the specific heat. So for example, one very important question, which is very interesting, is how basically what happened between the transition of a solid and the liquid. So when you increase the temperature, at a certain point, the specific heat goes down, and then it goes up, and then it goes down. So what happened at this point? Something, of course, we know that this behavior should be there because that's a phase transition, so that's totally understood. But how basically this is reflected in the dynamics of the collective mode and in the specific heat, it's much more subtle. So what we know is, for example, thinking back about our K-gap or our gap state, what we know is that basically at this point or around this point, the gap should close. Because on the left, we have purely propagating modes, shear waves, and on the right, we will have a gap state. And then we know that increasing the temperature, so moving here, the gap will open, and then at this point is exactly when the K-gap basically becomes the largest that it can. It becomes basically the Debye temperature, and then of course you cannot have any collective modes anymore. So then you are a gas, and in a gas, basically all the excitations are microscopic and are basically free particles moving. And that's how you recover basically the specific heat of the gas. Okay, so one thing which I find very interesting is the following. So if you go back to the idea of this instantaneous normal mode, and to my understanding, the original paper where this concept was, let's say, introduced is this paper by Svanvik in 1983. So you see, I just basically copy-paste what he says because I think it's very clear. And he says the following. He said, my picture is as follows. The liquid configuration remains in a cell, that's what he calls cell, performing approximate harmonic oscillations about the local minimum. So this would be basically elastic behavior, like a solid. And then he said, until it suddenly finds a saddle point and jumps to another cell. And then you will say this effect of jumping is basically what we see in the rearranging of the equilibrium position of the particle. And then he says, well, it's very likely, or at least it's, as a first approximation, one can think about a lifetime tau. And this lifetime tau is basically the lifetime of jumping. So how much you stay actually in this minimum, and then you jump. So the picture here is, again, the following. Is you have this minimum, and you oscillate around, and then at a certain point, you jump to another minimum, and you rearrange. And this jumping, so this tau that Svanvik called, is basically what I was picturing here, like gamma. Actually, gamma is 1 over tau. So gamma is the rate of jumping, tau is the time. And the first thing that when you read this paper, and you are aware about the ideas of Maxwell interpolation, Frankel, and that we discussed in the first lecture, it comes immediately to you that this looks like exactly the same story. Because the story of Frankel, it's exactly the same, or the story of Maxwell. The story is that at short time scale, you are basically oscillating, and that's what you're doing here. So if you are at time scales which are shorter than this tau, you will be just here oscillating, so you are solid, and then you jump. And when you jump, this is a liquid, because you are rearranging. So it looks to me that basically there must be a very strong relation between these modes here, these instantaneous normal modes, and the dynamics of the K-gap. Indeed, if you look carefully at the equation of the K-gap, what you realize is that it's true that there is a mode which basically, at a certain point, acquires a real part. So if you look at the real part in the K-gap, what you see is that there is nothing until a certain momentum, and then a modes appear. But you forget that there is also a second mode that I picture in the figure, which is purely imaginary. So the solution gives 2 modes. And there is one mode which at low frequency look exactly like this mode. And guess what? This gamma is exactly, at least in Maxwell interpolation, the inverse of Maxwell time. So this is, I think, something interesting that we should think more about it, because I have the feeling that these two concepts of instantaneous normal mode and And basically this Zwanzig idea, it's very related to the idea of Frenkel and of the K-gap that we discussed. Now, so this is basically where I almost want to stop today, and I want just to give you a very little summary of all these all I said in these 3 lectures, and then I will be very happy to discuss with you a bit more in details, or in general, you know, the complete picture that I try to give you in these 3 lectures. So the summary, at least from a theory point of view, is that you remember I started in the first lecture mentioning that there is this Italian saying that says that get lost, so perdersi means get lost, in un bicchiere d'acqua. This means in a glass of water. Okay, and this is usually a joke that we say to people: don't get lost in a glass of water. Now here, I want actually to convey exactly the opposite message. So the opposite message is that liquids, even if they are everywhere, or even standard bulk liquids, are still a very challenging subject. And especially from a theoretical point of view, very, very little is known. So there are many experiments, many simulations, but unfortunately, the theory, it's very complicated, and most of them are still very phenomenological. So here there is a lot of work for those of you who are interested in theory. I think there's a lot of window here to actually improve our understanding of liquids. And I think one promising direction here, it's basically to, you know, to connect different things that people at the beginning were not connecting. So if you think about, for example, the idea of K-gap is somehow the idea that you can understand liquids using, let's say, concepts from solids. And then here I show you a totally different perspective, which is coming from basically purely relaxational dynamics. And it appears quite clear that these kind of things must be related. And also, importantly, as Oleg mentioned several times, this can also have a lot to do with basically solids which are not perfectly ordered, but basically solids which contains defects. And the dynamics of these defects is actually important, and it can lead to behaviors which are actually very close to liquids. And I think I will stop here. So let me just say that I want to thank one more the organizer, and especially Oleg, to give me the opportunity to give these 3 lectures. It was fun. I learned a lot, and I hope you also learn a lot. And now I'm happy to, you know, discuss with you and be able to answer any question you have. Thank you.
Matteo, thank you very, very much for exciting lecture and information again. And I'm very glad to see that Sergei Dmitriev now with us. And I would like to give the information that our paper concerning heat capacity for FPO problem is accepted, but in Russian, but Matteo is quite the same subject, I would like to say. And let me start the discussion. Matteo, my understanding from the beginning of your talk today is the following. When you are considering the normal modes in liquid, it's in fact traditional statements for consideration of the appearance of some collective modes in liquids that could be recognized, for instance, in the Binar problem, when we have the Sommerfeld, and when we consider the stability of normal modes, we could observe in a liquid some vortices that could be considered as new degrees of freedom. As a consequence, we have change of the density states. It's true?
Yeah, so let me say that I'm not so sure that there is a simple way to connect what I said, so the instantaneous normal mode, with the presence of string-like excitation, like vortices or these kind of things. At least I'm not aware of a precise relation between the two. So I know that there are a lot of theories related to the strings-like excitation, not only liquids, also, for example, in glasses, and they have a very strong impact on the density of states. But I'm not aware of any paper that is able to derive these linear in frequency terms from vortices. So if you know, please send me. What happened? Can you hear me?
There is some problems with sound and video.
Can you hear me?
Yes, here.
I'm sorry, I don't know what happened today.
Okay, let me please, Matteo, I'm sorry because it was the problem technical. Let me continue concerning my questions. But the extension of degrees of freedom due to the, for instance, vortices in the classical analysis in the term of normal modes in hydrodynamics, it's not the way, it's not exactly the change of the density of states in our spirit. I would like to clarify my point of view. For instance, when in 2 weeks we will present our presentation concerning experiments, where we plan to observe some collective modes related to quasi-plastic flow in liquid, due to the concordant motion of group of molecules as defects. Yes, and due to this phenomena, we have planned to observe hydro and sonoluminescence due to the experiments. But when we are talking, because for instance, when we have some vortices due to the liquid instability, it's not change of the heat capacity, okay? It's not the change of the heat capacity, because we have the same Navier-Stokes equations with the same definition of the heat capacity in the binary problem. Yes, it means that we need to consider really another mechanism of relaxation due to the new degrees of freedom. You see, when Frenkel told in new kinetic theory of liquid books, he discussed the following: that because there are no sharp difference, qualitative difference between solid and liquid, the number of degrees of freedom for intermediate state of transition from liquid to solids must include variables related to liquid and solid states. But variables for solid states is defects, because defects provides plastic flow. It's my understanding. What about your opinion concerning that?
I see. So you're basically saying that these defects or vortices acts as scatters for this way. So they produce more relaxation mechanisms because of basically the presence of these new modes. Yeah, I never thought too much about vortices, so I have to be honest. I don't have anything smart to say, but actually related also to what you said before. So the Fermi Ulam pasta chain. That's why I was insisting on trying to see what happens there also for say the density of states or the specific heat, because there you have breeders, and breeders can act as defects and scatter your phonons. And
Yes.
So the question there is, can it be that basically in those kind of model you will see a behavior which is quite different from a standard harmonic solid? So for example, what will happen in the density of state? Or do you get some feature that resemble a glass, for example, where you have some kind of structural defects there? So my understanding that is, for example, a very interesting model, because it's a model that you can actually solve, and you can control the unharmonicity. So you can really check what is the effect of unharmonicity. And you see today, I insisted a lot that basically the microscopic reason why these relaxation modes are there is unharmonicity. So unharmonicity is the main microscopic difference here. And so my suspect, but I'm not expert at all in those kind of models, but you guys are, so I'm basically asking you, it's like that in those kind of model, if you crank up the unharmonicities, you should go away from what you expect in a solid and more close what you expect in a liquid.
I agree totally with you. And okay, and maybe Sergei Dmitriev will have some comments concerning this situation. Sergei, are you in touch with us?
Yes, I'm here. So, yes, first of all, we are very much interested in implementing all the ideas provided by Matteo in these lectures. Unfortunately, I had no time. These days, I was completely the craziness, some craziness. Okay, I don't think you want to hear my excuses, so let me come straight to the point. So we are going to continue this research, of course. As for that paper, it's a good news that it is accepted. Of course, the level of journal is not as high as we could publish these results. But okay, we were a bit unlucky with the referees. The referee said that this was done, which is not true, because I know all the works and cited in our work. And the referee mentioned one of the works we cited and said that everything is done there, which is not true, of course. But polemics in this situation maybe is not a good way to go. I think we just add more results. We add larger amplitude of phonons, because what we have done in that paper is phonons of extremely small amplitude. We took it as small as possible. Why? Because we wanted to avoid such effects as interaction of effect of phonons on discrete breathers. We took very small amplitude just to minimize the interaction, kind of interaction or kind of effect of phonons on discrete breathers. When we increase, we still keep it small, but we increase it 10 times, let's say, because the amplitude was 10 to the minus 3, I guess. We can take it 10 to the minus 2, which is also small, but it is sufficient to see some effect of phonons on discrete breathers. The effects are breathers will start to accelerate. They will be accelerated due to the pressure from phonons. This is first. And second, breathers can start to radiate energy. So when we add those effects, we are safe to submit this paper to a good journal, because I believe this information is new, completely new, and so on. So we should continue this. And of course, I'm very much excited about these gap states. And yes, we have discussed it many times with Oleg. And my feeling is that when we increase temperature, as Matteo says, we increase nonlinearity. When we increase amplitudes of of atomic motion, which means we increase temperature, we do increase effect of nonlinearity, because nonlinearity starts to work at high amplitudes, and the higher the amplitude, the stronger is effect of nonlinearity. So we consider high amplitudes when we expect thermally populated discrete breathers to appear in the chain. And those breathers, they kind of cut the system into pieces, because the phonon free path will be just the distance between nearest large amplitude breathers thermally populated, which means that in the spectrum, long waves will disappear. We will not have very long waves. We will have only waves, maximum length will be the distance between nearest breathers. And this means that we will not have phonons of long waves near zero K vector. And I believe this can be considered as a gap. Maybe my understanding is too poor and I'm going in the wrong direction, but I want to check this. And if it is so, Matteo will judge and say, is it that gap or a different kind of gap or anything. So this is what we want to do and to discuss with Matteo in the near future. So, okay, let me stop here.
Thank you very much. Matteo, what about your possible response concerning that?
Yeah, it looks extremely interesting from my point of view. There is also one other point that I would like to stress. It's like I'm curious to see if so if I understand well, when you are at small amplitude or basically small momenta or small frequency, these phonons are less scattered by these breathers, and so I would expect that, for example, in that situation, the density of states at low frequency would be pretty much like Debye, like a solid, but there at a certain point, increasing the frequency, you will increase the interaction between the phonons and the breathers. So the phonons will be much more scattered there. And it would be very interesting to see if you see something in the density of states, like, for example, in glasses. Like, in glasses, you see a peak over there, which is called boson peak, which is usually, well, there are many theories related to these things, but one of the theories indeed that basically anharmonic defects, or basically defects that comes in glasses because of structural defects, basically scatter away these phonons and increase the relaxation, the attenuation of sound there. Now, in our situation, the defects are not structural, but are basically given by anharmonicity. So when you have anharmonicity, you have these new modes, and this new mode acts as scatterer for the other phonons. So it would be interesting. Actually, I would like also to ask you guys what is known about, for example, because I know that all the story of Fermi-Ulam, pasta models, and whatever comes from basically thermal conductivity and this kind of relaxation, equilibration, etc.
Mm-hmm.
So I was searching and I found few papers, but maybe I will send them to you again. Where
yes. I remember you have sent those papers. Yes. Thank you. Yeah, if you send it once again, it would help a lot, because my email box is just a mess. Okay.
Yeah, I will try to do that, because I was interested to try to understand, because what I want to understand is the following, basically. So you start from the simple situation, which is an order solid, perfect order solid, like textbook.
Mm-hmm.
And there you understand everything, very easy. Now, you start to increase anharmonicity, okay? And we know that at a certain point when anharmonicity is huge, for example, at very high temperature, you become a liquid. So you are totally different from a solid, and we know what happened in a perfect liquid. Now, in the middle, there should be a transition. And this transition, of course, we know also that glasses are kind of middles between liquids and solids.
Yeah.
So I would not be that surprised that if you take your Fermi-Ulam pasta model and you increase anharmonicity more and more, and the amplitude more and more, and basically interactions between these defects and phonons, you will see really basically deviations from the standard order solid, which maybe actually, by the way, are not that different from what also Oleg has in mind with dislocation and disclination, because also dislocation and disclination relax the phonons. So in a way, maybe it's not so different. I don't know. I have to think more about it, but it's something that is definitely worth to investigate.
Okay, yes, I totally agree. Our next step is just to calculate Phonon density of states at different temperatures and see the evolution. And we have some experience in that. And I know that yes, long waves disappear from the spectrum. And Matteo, also you mentioned that long waves are scattered most by discrete breathers. This is only true for hard type unharmonicity. We can make a model with soft type unharmonicity with on-site potential. Then the situation is just opposite. Then short waves go through breathers and long waves are scattered by the breathers. So we will, of course, compare these two different cases and it will give additional information. So we are going to continue this, and I would like to closely discuss it with Oleg and Matteo, because yes, you are an expert in many things which we are not. So
I have one question regarding what you said. So which kind of unharmonicity do you think is more relevant for a liquid, the soft or the hard?
I don't know, have no idea. But we will study both, because we have two different worlds in the world of nonlinearity, like black and white and like soft and hard unharmonicity. And what is all the effects are usually reversed. So it is interesting to compare. And then you have experience with glasses or liquids. You can say what looks familiar to you.
I totally agree with the feeling of Sergei, because may I repeat again the sentence by Frenkel concerning the possible way to describe liquid solid transition, because in his famous book, Frenkel wrote that the degrees of freedom, if we need to describe transition as continuous transition from a liquid to solid state, must include variables related to the liquid states and variables related to the solid states. But variables related to the solid states is defects. And as a consequence, I think for intermediate states, we have both soft and hard. Because if you recall, for instance, Franken Kontorova model for dislocation, yes, due to the soliton-like Frankel model, is really hard. It's really hard. It's true.
Actually, sinusoidal on-site potential in Frankel-Kontorova model is soft type potential. But we can choose a different profile, not sinusoidal, but different profile. Then we can achieve hard type nonlinearity. I'm talking about model with harmonic bonds and unharmonic on-site potential. But we can also include unharmonicity in the bonds, in the interparticle bonds. And again, we have choice. It could be soft or hard. So we have actually 4 different models we may have. We take on-site potential, soft or hard, and we may take interatomic potentials or interparticle potentials, again, soft or hard. So we have 4 different combinations. Maybe eventually it is better to study all 4 of them with different magnitude of unharmonicity. And harmonic means 0 unharmonicity. So what we have done for different types, you see, when we have Fermi-Pasta-Ulama, we only have interparticle potentials and we have zero on-site potential. In this case, we mainly have just hard type unharmonicity. So I think all cases should be analyzed with utmost care, and comparison will give us a lot. Every model will contribute to the understanding of what is going on.
Okay. Let me please short comment containing the following, because another audience probably has also questions. I'm worried very much concerning, I'm thinking with my colleagues concerning experiments that we try to trigger maybe this year concerning observation of hydro and sonoluminescence due to the very intensive flow in the boundary layer of oil or water. Probably mainly it will be oil, because in this condition for high strain rates near the boundary, this phenomena like hydro and sonoluminescence is observed. But my feeling is that this kind of the signal, high energy signal, could be produced by the carriers with high energy. Of course, it's like micro shears or dislocation, something like that, which provides a qualitative new mechanism of momentum transfer related to plasticity. It's the goal of our experiments, it's development of experiments that we realized after Sakharov's statement due to the explosive wire in liquid. It's our goal, and when we will finish this cycle of lectures, it will be in 1 week after Bill Proud, we will prepare our presentation concerning some theoretical view at experimental setup that will try to trigger, to observe this gap momentum states phenomena according to our feeling. It's my expecting what we can do in the near future. And maybe our colleagues will have some questions. Please.
Yes, thank you for the very interesting trilogy of lectures. And I have a question, maybe in continuum of discussions. In studying of the behavior of materials, we must take into account one more factor, an additional thermodynamic variable, pressure, because at high pressure the gas becomes a liquid, and how can we affect the stresses, maybe internal stresses, be taken into account?
Okay.
I don't see, maybe Matteo don't hear.
Matteo, yes, are you in link with us? Probably Matteo has some problems.
Yes, maybe he don't hear.
Okay, not so good connection with Matteo today. Okay, but Yuri, you could ask, at least articulate for us.
Нет, Олег говорит, что тут же это давление, это же еще одна определяющая переменная термодинамическая. Потому что фактически можно...
Matteo, in the links. Please, Yura.
I'm very sorry. So I heard the question about the pressure. So yeah, I totally agree. In my talk, I didn't mention too much pressure, mainly because I don't have any result. But it's definitely something very interesting. So for example, one can try to understand the effect of pressure instead of temperature. And as you said, you can move pressure and pass from liquid to solid. So you can try to understand. Usually pressure increases harmonicity. So if you increase pressure, you increase harmonicity. This is known, for example, also in these high pressure superconductors or things like that. So it's not surprising that putting high pressure, the dynamics becomes that of the liquid. So I think this is expected, and I totally agree with you that one way also experimentally to increase basically an harmonicity is actually pressure.
Okay, thank you.
But Yura, pressure or shear stress, it's not the same.
Yes, of course, we have to take into account all stress tensor for difference influence of hydrostatic and non-hydrostatic parts of tensor. But it's a question how to include the influence in equations for different parts of stress. For example, for hydrostatic stress and dilatory part of stress. Yes, of course, it's different influence of two parts.
But that's actually also why I mean, the idea of Maxwell interpolation and Franklin interpolation is nice, but it's too simple because you cut out from the Navier-Stokes equation the effect of pressure. That's too simple.
Yes. Yes.
So that can be true when pressure does not play so much role. But when the gradient of pressures are actually very large, then you cannot just kill that term. You have to consider it. And then I don't know what will happen to your gap momentum state, for example.
Okay. And let me please maybe some cooling remarks. I recalled our discussion at Los Alamos laboratory with Vasily Bulatov and Bradley Holian, when we tried to recruit all computing opportunities of West Coast, yes, to observe in generation in the crystals of dislocation ensembles, yes, due to the MD simulation or ab initio simulation. And of course, they observed numerous dislocations, but the number of dislocations, according to the opportunity of computing after recruiting of West Coast, was not enough for a representative presentation concerning density of states in the presence of dislocations. And as a consequence, it was the conclusion of our discussion. We need to combine or to develop statistics and thermodynamics to include initially mesoscopic defects like dislocation to determine the density of states. It's results that is a little bit cooling me concerning possible opportunity to estimate, for instance, specific capacity from simulations. I remember this. Sergey, what about your opinion?
Okay, I turned on the sound. So yes, of course, Oleg, I agree, and let's move in these directions.
Okay. And colleagues, please, another question to Matteo or another person participating in discussion. Okay. And let me please to conclude that in 1 week after the finishing of lecture by Bill Proud, it will be a seminar initiated by our lab when we propose some theoretical view concerning transition from liquid to solid from a relaxation point of view, and how it's possible to relate to gate momentum states, but mainly concerning experiments that we are carrying out to investigate this solid liquid transition, and future experiment concerning observation of hydrate sonoluminescence in boundary layer of intensively intensive fluid hydrodynamics. It's our plan. And no, at least for us, this plan is exciting, but I hope that we could deliver these ideas to our colleagues. Okay. Matteo, thank you very much for exciting cycle of lecture, and it's very stimulating for us.
Thanks to you for listening and for inviting me. I hope there will be an occasion soon to actually have also a dinner or a lunch in Russia together.
Yes, of course.
Yeah.
With Sergey participation, of course, Sergey.
Please come to Ufa, or we can go to any other place. Yes, sure.
Sergey, at the beginning, we established this dinner in Perm.
Okay. So, Matteo, you are now in Shanghai. Am I right? In China?
Yes, you're right.
Okay. Is it okay to travel to China now? No problem?
No, they don't let you in. If you don't have a work visa, the barrier is closed. You cannot come. Otherwise, I would invite you. But unfortunately, with this pandemic now, it's a disaster.
I see. Okay.
As everywhere. Okay, dear colleagues, thank you very much for very fruitful and marvelous discussion. Matteo, thank you personally.
Thanks again to you.
All the best. To be care.
Likewise.
Thank you. Goodbye.